we're going to study a kinematic situation that's easier than this one. We looked at this on Friday in class, and our job is to notice the change in motion, velocity, and acceleration throughout for the car in this short scene. So we started at rest, floored the gas. Here he goes. He's approaching the short ramp, 95 miles an hour. Boom. Okay. Now from this point, we looked at this in class. He had an initial velocity coming along the road. For a very short period of time, he was on the ramp. Then after the ramp, the vehicle's in projectile motion. We noticed in class that this velocity here was 95 miles an hour, but that contributed a little less horizontally and quite a bit vertically. So he hits the ramp at 95, and he's going 95 miles an hour here, but at an angle. 95 miles an hour at an angle is slightly slower horizontally and slightly slower vertically than 95. So what happened? Horizontally, I have graphs set up here with two vertical lines indicating the three phases. This is his time. Time is the horizontal axis. Position, velocity, acceleration. This is the time it takes to approach the ramp. This is the short period of time on the ramp. And after this, this is the time when he's a projectile. Well, he started, let's say, we'll call his starting at 0. That's where the coordinate system starts, right where the cops were. He had no velocity to begin with, and his acceleration had to have been positive. We'll call positive forward. And for us, our kinematic equations all deal with constant acceleration. So I'm going to assume that's a constant positive acceleration forward by the car. His velocity constantly increased. So that's a linear, call that linear upwards. The slope is equivalent to, that's a positive constant acceleration, positive slope, corresponding positive slope, and this, and his change in position is a parabola. I think I can make a better one than that. Parabolic upwards. All right, I'll leave it at that. Parabolic upward position change. And while he's on the ramp, because he's at the top, he's going slightly slower in the horizontal direction than he was approaching the ramp. The acceleration in the horizontal direction must have been negative in that time when he was on the ramp. So a negative acceleration drops his velocity in the horizontally in the time he's on the ramp. He's still going forward, so his position doesn't. He doesn't start moving in the other direction, but instead of this positive region where this region of positive acceleration where this is a concave parabola upwards, this is now a concave parabola downwards. So there's a little bit of a curved slope. It's still going up, but it's concave downwards. All right. Now let's consider the vertical direction. He's on the pavement, we'll call that 0, and he remains on the pavement until the ramp. His velocity, his position's not changing, so his velocity mustn't change. It was 0 to start with, and it remains 0 until the ramp. No change in velocity, so the acceleration must have been 0 until he hit the ramp. He was stationary in the vertical direction at the bottom of the ramp. At the top of the ramp, he was launched upwards. So he must have had a brief positive acceleration to be launched upwards so rapidly at the top of the ramp. And the acceleration, once he's in the air, well, let's look what happens. Actually, let's do the... so his position went rapidly higher as through the ramp, in the time through the ramp. Boom. And his velocity... Actually, that should have been parabolic upward. His velocity rapidly increased as he went, and yeah, that should be a parabolic upward. All right. Let's look at what happens after the ramp. I think we all remember. There's a long parabolic arc until he reaches the ground. So in the x direction, while he's in the air, his wheels nor his brakes are touching. He has no way to accelerate horizontally. So he must have no acceleration. And no acceleration means a constant velocity in the air. A constant velocity means a constant slope. So he continues to move ahead with a constant slope equal to, and it's off the graph here. You can imagine what it is. It's linear upwards with a slope of linear upwards with a slope equal to the this is parabolic upwards. Let's think about what goes on in the vertical direction as he arcs through the air. He must have a negative acceleration due to gravity. All objects do when they're in the air, and they're projectiles. All projectiles have a constant... This is supposed to... that's rubbish. All objects are supposed to have a constant 9.8 downward, meters per second downward. What does that do to his velocity? It reduces it. So his velocity is reduced. He starts with a large upwards velocity coming off of the ramp, and that velocity declines. It declines towards zero, and it continues to decline downwards until it's downwards as he comes down from the top of his arc. The position, the velocity starts to decrease, but in this period of time, it's still an upwards velocity. It's just a declining upwards velocity. That's because this is a parabolic downwards. I'm going to have to become better at these electronic pens. All right, and this point of zero, at the top of the arc, he has zero vertical velocity. As his position comes down, he must have a negative velocity. As his position continues to rise, he still has a positive but declining velocity. Okay, see if you can't make sense of those graphs, maybe watching, listen to me once or twice, and hopefully you can reproduce something like this in a slightly easier situation in the upcoming quiz.